Okay, one more example of the type of graphing that we want to know how to do. This is sketching a graph. This one, f of x, is 2x squared minus 2 over x squared minus 9. And we want to go through, we want to be able to determine our domain first. So we're going to look at where the denominator is equal to 0. And we know that x squared minus 9 is going to equal 0. Let's see, x squared is equal to 9 at x equals plus or minus 3. So we're going to state that our domain will be the set of all real numbers except at x equals negative 3 and x equals positive 3. Now the next thing before we start finding any vertical asymptotes is that we should try and factor our numerators and denominator as much as possible. So I'm going to rewrite f of x this time. F of x is going to factor in our numerator as 2 times the quantity x squared minus 1. In the denominator, we know it's going to become x minus 3 times x plus 3. And one more factorization is going to give us 2 times x minus 1 times x plus 1 divided by x minus 3 times x plus 3. Now, right now, we know that that means that there are no common factors. And since there are no other factors to reduce, we can conclude that our vertical asymptote is going to occur in 2 places this time. One at x equals negative 3, and another at x equals positive 3. So I'm going to go ahead and sketch those in using some vertical dashed lines right here. One at negative 3. So we can do a reasonable job of following the line here. One at x equals positive 3. Again, label everything completely. Vertical asymptote, x equals negative 3, x equals 3. Next, let's look for our horizontal asymptotes. Horizontal asymptotes occur on functions where the degree of the numerator and denominator are the same at the quotient of our leading coefficients. In this case, that's the line y equals 2. Well, 2 over 1, but that's 2. So I'm going to draw my horizontal asymptote along the line y equals 2, going left to right. So I've got a horizontal asymptote at y equals 2. So next I want to look to see if I have any x and y intercepts. Well, y intercepts occur wherever x is equal to 0. So our y-intercept in this case looks like it's going to occur by substituting in 0 in place of x, which gives us negative 2 over negative 9, which is 2/9. So 0, positive 2/9. That is a very small positive number, but it's pretty close to somewhere between 0 and 1 there on the lower side of that. What about x-intercepts? Well, x-intercepts occur at any points where the function itself is equal to 0, but really the place where we need to look is where is the numerator equal to 0. I've already got my function here in a nice factored form, so what happens when we set it equal to 0? Well, only the numerator matters, right? We just would want to know where 2 times x minus 1 times x plus 1 is equal to 0. So, if we set each factor equal to 0, we find that x equals 1 is such a place, and x equals negative 1 is such a place. And so our x-intercepts occur at negative 1, 0 and positive 1, 0. I'll plot those here And here it looks like there's something interesting happening right here. And in fact, we should check for symmetry. If we check for symmetry right here, we might note the following. F of negative x is the same thing as negative x quantity squared. 2 times negative x quantity squared minus 2, divided by negative x quantity squared minus 9. Squaring negative x is exactly the same as squaring positive x. So in other words, it's equal to 2x squared minus 9. Minus 2, not minus 9. It's x squared minus 9 down here. And that is equal to our original function f of x, and therefore this is an even function. Now, the reason why that's really, really useful is that in an even function, whatever happens on the right-hand side of the x-axis occurs equally on the left-hand side. It reflects about the y-axis. That's really, really useful. So what we're going to do is that means if we want to determine the behavior near the intercepts, we should just go through and just substitute in values from one side or the other. So I'm going to go for my right-hand side. And I've already know what's going to happen at x equals 1. Let's go out to x equals 2. Substitute that into our function to find out what's going to happen. Well, at x equals 2, y is going to be 2 times 2 squared, which is 8 minus 2, divided by 2 squared minus 9, that's 4 minus 9. And so this is to say at 6, negative 5, negative 6/5, which is a number slightly greater than negative 1, except on the negative side, so I'll put it down here. Of course, whatever happens on the left happens on the right in an equal sort of way. So we kind of get a picture of what's going to happen right here in the middle. What happens at 3? Well, that's a vertical asymptote. Same thing with negative 3, so we don't need to worry about it. But what happens at 4? Well, we'll try 4. Remember, that's 2 times 4 squared minus 2 divided by 4 squared minus 9. Well, it looks like we're going to get a positive number first of all. That's going to be 2 times 8 minus 2, which is to say 16 minus 2, 14, divided by 16 minus 9 sevenths, that's equal to 2. So this graph passes the point 4, 2. Wait a minute, let's try that again. 4, 2 times 4 squared, 2 times 16 is 32 minus 2. That's 30, pardon me, divided by 7. That's actually greater than 4, right? That's like 4 and 2/7 more. My apologies here. Almost made a mistake. Could have given somebody a bonus point off of that one too. Wouldn't that have been fun? Sorry about that. 4 and some change right here. All right, 4 and some change. I'll go ahead and write it as 30 over 7 just to keep it copacetic. So 4 and a little bit more than 4 right here. There we go. If we go out to 5, I'll just do it one more time. We're going to have 2 times 25 squared minus 2, that's 48. And we're going to have 5 squared minus 9, that's 25 minus 9, that's 16. Well, that one reduces. Let's see, 48 divided by 16, well, that's 3. Ooh, that's really nice. 5, 3 is another point on this graph. I've already got sort of an idea of the behavior. Of course, whatever happens on the left happens on the right. So at negative 5, we'll also get positive 3. And graphing our line, it's got to come across this horizontal asymptote, go up towards positive infinity, come along our vertical asymptote so that it can pass through these points right here, and it will look exactly the same on the left as it does on the right. So any behavior that we did on the left-hand side, we're going to mirror on the right-hand side. We're going to come up with a graph that looks similar to this. Okay, more to come in the next video.